precision multiple access code channel. In our topic, we have as objective is to combine access, line, and error correcting code through the challenges of good cardinality, multiple access interference, and obviously asymmetric error correcting code, which will be our main contribution. And we want to apply it over the optical fiber loop. And for us to reach this kind of objective, using this application, we needed first to define our model. And from our model, we identify some problems whereby we come up with some solution in 3 points. And as you can see, the second solution is what we were supposed to present. Is what is written in the manuscript. And then we come up with the syndrome decoding as last solution. Our model, as you can see, is just a combined modulation coding. We have a fast frequency modulator that is based basically of brackets, and we have also a unipolar modulator that is the optical orthogonal code. In this model, we only focus on unipolar modulator code. Why? Because it's where our error, asymmetric error correcting is embedded. We identify some particular issue in what we call problems. The first one is that when we use drag ratings, once a frequency is taken, it's no longer available. In the other hand, using the photodiode detection with a non-coherent scheme, we have another issue that is the bit noise. The bit noise actually is a component of a short noise that we all know, but in light it's called dark noise. It takes forms, it becomes significant when the traffic becomes higher. When we have a higher traffic, and it becomes significant, and it has the effect of absorbing light of a certain intensity. So this effect will transform the channel into a Z channel, and therefore we need an asymmetric correcting code to go forward. As a solution of it, we choose to construct an NW1 optical orthogonal code. Actually, the solution is not new. There is a lot of solution already in that field. But we thought regarding the constraint of our application, we needed a more flexible solution that can accommodate a lot of congruence classes. It's what we did, because when you look at this power spectral density map, is not normalized within a period. We can find that as the length increases, the power decreases. But the correlation property, in the middle does not change. We still have correlation 1 over the same period. Then we can go forward to construct our code. To construct it, we need some convention. As the first convention is how to locate it, is the bit position. Let's take this code, vector. We can see that the first way of the code is at position 0, the second at position 1, and the third at position 3. So those are the bit position, and we will focus on those bit position to give our solution, to come up with a solution. But there's another consideration we call block, consideration of block. Since we want to use a combinatorial solution, we call the combinatorial solution can be viewed as a family of blocks, and each block will become a code word. And such a block then will be the subset of bit position 1. And in this example, we have a family of 1 block. But also, we stated that we have a problem of cardinality that need to be addressed. So the block that we call in our sense block are the one that will be full orbit or full orbit. That's what it means, that if a block is of length n, it will provide us with n code word. So those are the consideration we will have, and then in mathematical representation it can be done like this, and mostly we can give a definition of our combinatorial solution. Our combinatorial solution, we say that is based on difference of position. Okay, we say that a code, an optical orthogonal code, as described here, will be considered as, because we have already W weight as Hamming weight, so we will have W minus 1 subset that will be the difference point, and it's called neighbor in our difference of position. It means what? It means that if we go to this example, we have this code as we took at the first place. The difference of position, we have the first neighbor, that means the one that comes directly, and then we have the second neighbor, that one will come after. Directly, that means I move from position 1 to the next position 1, and so on. The second neighbor will be first position 1 and the second in the line. But then the code is a code with a good correlation property, as we saw in the graph. So we need to keep that property. Then we need them to redefine what is called correlation. And we say that the code will have a good property in terms of correlation if the difference of position, or let's say the neighbor, with each neighbor will be represented at most once. So in that way, we can have what we call a good correlation property. But we don't limit at 1. In our case, we only take 1, but actually it's like this, and you can verify it if you reach home. Now, our problem was then to define all the classes of congruence that will allow us to perform our code. We need then to optimize the length of the code. That means we needed the lower bound and the upper bound. If all the weight of the code, all the difference of position, that means all the neighbor are in such a way that the difference is always the difference of the previous plus 1, or the last one plus 1. If we go in that sequence, that will give us the minimum length of the code. It's just like we choose to put the policemen in each and every intersection than putting them in the equidistant position of the intersection to where. So by approaching them one another, we are sure that we will have a better configuration. And then we have the upper bound. The upper bound is given to us by Johnson bound, which is the normal combinatorial of picking the weight over the n code length. That will give us this solution of the maximum length, as you can see here. And then that will lead us to the first proposition. The first proposition says that for any family of blocks, we have L blocks, that means L code word. The code length will be always bounded, and those are the bounds of the code. So this, we can go through this example, putting in the mind that each and every difference of points will be only taken once. So in this example, we took the first now let us go at the topic of today. What we wanted is to correct the asymmetric error that has occurred. We say that the code is T asymmetric corrective error if it can correct up to T errors, and then there exists an existing rule that will allow us to recover each and every weight, each and every one lost in the code. We have then some properties. We have to adapt the optical orthogonal code in the properties of an asymmetric code. First of all, we say that the number of positions in the code, in two different code words, will be changed into 0 and 1, are always given by n, the function of n of those codes. And then if we are in the optical orthogonal code, regarding the bond that we have here, at this level, we always have this number is between W minus 1 and W. The same thing, the asymmetric distance, which is an important metric for asymmetric code, it will be always in this bond, and also the Hamming distance as related to the asymmetric distance. It will be always in those bonds. So
you have 2 more minutes.
Most importantly, the vector that we change into 0 are the one we want to cover. So we need then a proposition, a second proposition that says an NW1 optical orthogonal code can correct W minus 1 asymmetric error. So this can be proved by taking this example down here. All the two code vector, and those two code vector we have the set that we have changed from 0 to 1 and 1 to 0. The intersection will be always empty. And then we need them to retrieve those to retrieve them at the reception side.
Floyd, please.
Okay, good afternoon. My name is Dadiso Sarua, and I'll be talking about spectral shaping code with error correction capability. Alright, so firstly I'll give a brief background, then I'll talk about DC3 codes, then interleaving DC3 codes, the effect of interleaving on the spectral shaping properties of DC3 codes, then some results I got from that, then DC3 interleaver design, then the result I got from that, and then the effect of interleaver parameters on notch width, and then finally I'll look at the future. Okay, so for a brief background, spectral shaping codes, they are basically digital codes which are designed in such a way that their alphabets give rise to a predetermined frequency spectrum analog. Then the examples they include, but then they're not limited to DC3 codes and spectral mouse codes. Then the applications, they're used in magnetic recording systems such as CDs. Okay, so for spectral shaping codes, there's a region whereby the frequency spectrum is suppressed, and then it is known as the notch width. Okay, and then it is measured, or it is characterized by the cutoff frequency omega 0. This frequency is obtained at the point where the power spectral density function is equal to a half. Okay, so figure 1 shows an example of the power spectral density function of a DC3 code book. Okay, so from this figure, you can see that the notch width is approximately 0.1. That would be corresponding to the point where the PSD function is 0.5. Okay, then I looked at how the notch width of DC3 code book varies with the code word length n for a given order k. So the general result which I obtained was that as the code word length increases, the notch width decreases. then so I investigated the effect of interleaving the DC3 code on the spectral shaping properties of the DC3 code. So I used matrix interleaving, and then I was varying the interleaver parameters J and W, where J is the interleaver depth and W is the interleaver span. Okay, so let N be the covert length of DC3 code book. So I did the investigation in the regions J is less than N, J equal to N, and J greater than N. Okay, so the results I got in the region J is less than N. There are certain selections of J and W which gave rise to a DC3 interleaver output. So in general, odd J and odd W values they gave rise to a non-DC3 output. So from these two observations made, it could be concluded that to get a DC3 interleaver output, elimination of all JW combinations which consist of either odd J, odd W, or both would result in a DC3 interleaver output in this region. And then I looked at the region J is equal to N. So in this region, the interleaver output is basically the transpose of the input code book. So from how a DC3 code book is designed, the transpose of the code book will also be DC3. So the output was DC3. And then in the region J is greater than N, for all the J values in this region, the output from the interleaver was not DC3. So the DC balance was lost in this region. Okay, so here's an example. So the input here is DC3 code book of order K is equal to 1, and code with length N is equal to 12. So in the region J is less than N, in this case the J is equal to 6. This figure shows the output power spectral density function from the interleaver output plotted on the same axis as the power spectral density function of the input code book. So you can see that the output power spectral density function is DC3, though the notch width is much smaller than that of the input code book. And then for J is equal to N, the interleaver output was also DC3, and the notch width was slightly greater than that obtained in the region J is less than N, but then it's still much smaller than the notch width of the input code book. And then in the region J is greater than N, okay, the DC balance was totally broken, so the output was not DC3 as shown in figure 5. Okay, so now the goal was to design an interleaver which gives rise to DC3 outputs regardless of the input code book. So this interleaver makes use of the zero disparity coding scheme. Then for even interleaver with that mapping given by that equation would give rise to a balanced code word in the interleaver. Like if you map the input sequence using that equation, then the first row of the interleaver will be a DC3 result. So the mapping basically takes one element from each input code word and enters it row-wise in a matrix. Then the resulting row which is formed will be a balanced word. Okay, so to get the subsequent rows which are also DC balanced in an interleaver, the depth has to be decremented by 1, and the input sequence X has to be reduced by subtracting the previously formed code word. Okay, and then so the zero disparity coding scheme only works for even number, even code word length. So for odd W, I use the results which I got from using this DC3 interviewer. Figure 6, it shows the result which was previously obtained in the region J is greater than N, which was not DC3. So after applying that mapping in my outputs, became DC3. Then I now look at the effect of the interleaver parameters on the outputs notch width. That's the notch width of the interleaver output after applying the mapping. So in the region J is greater than N and W is less than N, the notch width of the output was greater than that of the input code book. Then that is shown in figure 8. However, increasing J, the J value, it implies an increase in the notch width, but then it also implies an increase in the interleaver delay. So there's a trade-off between increasing the notch width and J, the J value. Okay, so picture web, which I'm actually currently looking at this, I'm now investigating non-binary DC3 code because the initial investigation was in the binary field. So now I'm investigating how the notch width varies with the alphabet size Q for a given N value. Then also how cardinality varies with Q for a given N. Okay, and then also investigating the effect of interleaving non-binary DC3 code. The end. Any questions?
Thank you very much. So we have time for questions. I have a question just out of curiosity. In many of your examples, we saw the parameter J is 29. It's not so common. Is there a special reason to choose that parameter?
No, it's just a random example I picked up.
Okay. No particular reason.
I just look for J less than code with length, J equals to code with length, and J greater. So it just peaks.
This peaks over.
Yeah. I can show all the figures.
Yeah. Any other questions? Not? Let's thank the speaker again. I would like to invite the last speaker to set up the presentation.
My server doesn't support the connection encryption data.
Doing an update to your email.
Yeah.
It means that the internet here has a problem.
Yeah, with the encryption.
Yeah.
So will I have to change the encryption?
They don't allow it. Actually, this is a standard thing that they allow. They give you.
They don't give you
Any options. I do have a USB dongle.
Okay, so as I said, the last speaker is also from the University of Johannesburg, supervised by Snaya Suhara.
Check your
I
email.
would like to give the floor to Martin Trollet.
okay. Good. Yeah.
Thank you. So I'll keep this on the
That would be good.
Yeah, but we have to be outside because here also doesn't pick up any signal.
And I'll be presenting my project thus far, which is called Narrowband interference signal detection by using a spectral shaping technique. So I'll give a brief introduction to spectral shaping and spectral null code. Then I'll talk about the problem, which is OFDM and narrowband interference. And then I'll talk about the objective and scope. And then the conclusion is more of my future work for the project. So spectral shaping was just actually introduced on my colleague here. So basically what happens with spectral shaping is we have a redundancy code. Usually the redundancy code is introduced for edit correctional purposes. But Godoc introduced a method where we can use redundancy codes in order to create a sparse spectral density with desired properties. So then a system can be designed according to these properties. And one example of this is the use of pilot stones on compact disks. Find the locations where this formula holds true. So as you can see in this code book, y1 plus y3 equals to y2 plus y4. And this holds for all the codes, and this is a quick plot of the fast spectral density for that code book. So now what will happen, so I'll quickly discuss the problem statement with narrowband interference and OFDM. So what will happen is narrowband So the presence of narrowband interference greatly reduces the performance of OFDM, and it affects in the area of a few subcarriers. And so we'll come to that bit. And also the energy is assumed to be an order of magnitude higher than the signal. So for the problem statement, one problem is detecting OFDM and how that can be done. So previously what will happen is narrowband interference will be detected by looking at where the spectral has an amplitude and maximum amplitude. This can be one estimate to indicate the presence of narrowband interference in the channel. Then we can apply adaptive notch filtering to cancel that, and various other split spectrum techniques can be used. So what I plan to do with this research is I want to see if I can detect the presence of narrowband interference by loading a subcarrier in OFDM with a spectral null code. So what has been done previously by Hamais, which he used to generate a spectral null code with like this. Then he'll remove the first code, which is all zeros, and the last code, which is all ones. So what he did then on the receiver side, he looked for locations where you would get all zeros and all ones. Since it's not in the code book, we don't expect to see that there, and then it might indicate the presence of narrowband interference. What he then did is he replaced the corrupted bits with a minimum handling distance code from the code book. It's not to recover data, but it restores the spectral properties of the system. So what I want to do is I want to go and load OFDM carriers of spectral null codes. Then I want to observe the spectral properties of the NPI after the narrowband interference was introduced in the system. And then this will be done by applying some spectral sensing. And then I want to see if it will be possible and how it can be possible to detect NPI introduced in the system. So this is a quick overview of my system model. So this is basically a normal OFDM system, and I added some white Gaussian noise and made use of the data fading channel. Then one important thing to notice about this is the modulation scheme. This will be binary phase shift key, because spectral null codes will only be applicable for that case. Then at the end is the important part. So here I'll apply the power spectral density detector, and I'll sense the spectrum and see what happens when NPI was introduced. So there's a quick summary of what I discussed. So I spoke about the spectral shaping techniques, how it introduced desired properties in the spectrum. And I introduced narrowband interference, how that affects OFDM subcarriers. And then my research objective is to load OFDM carriers with spectral null codes and investigate how that will affect the spectral properties.
Martin brought us back to schedule. Presentation, but we have room for some questions.
I have one question. Yes. Because your work is work on for the narrowband interference.
Yes.
So what is specific application you target?
So at the moment I haven't investigated that as of yet.
So what kind of application? Like a power line communication?
So at the moment I'm focusing on the wireless environment. That's why I use the daily fading channel.
Exactly. Because I saw you use the fading channel, so I don't know.
Yeah.
But there is a narrowband interference exist in that channel?
Yes, I'll have to investigate how that will be introduced in a channel like that.
Okay.
Did you look at other methods?
So for detecting narrowband interference, yes, I looked at the methods where you analyze the spectrum. So we expect to see a peak in the spectrum where we usually get narrowband interference. So that's one method. I'm just investigating an alternative method.
Because there exist alternative methods.
Sorry?
There exist alternative methods.
Yes, yes.
You should compare.
we understand the interference bandwidth should be way smaller than the total transmission bandwidth.
Yeah.
Can you quantitatively say like 5% or 10% or 1%?
No, not at the moment. So it stands between like a few subcarriers, and that's the assumption I'm going on.
A few subcarriers.
Yes. So usually, depending on how many subcarriers and type system queues are, what will happen is if you compress it more into the same bandwidth, you expect it to expand over more subcarriers.
Okay. Thank you.
Okay. No further questions then. Thank you once again, Martin. That concludes this session. We now have a half an hour break.
It's very good.
We need it.
So, but I can really find crypto in this email, right? I can really find my crypto.
Could you update your emails?
No, it was no. I cannot. It's blocked.
It's because of the internet here. Just a
Yeah,
second.
but
Popularize them by showing that they could attain a Shannon, that they had a Shannon limit performance. Since then, a lot of research has been done on these codes for the applications that range from telecommunications to storage devices. Now, these codes, QCLPC code stands for quasi-cyclic LPC codes, and were discovered by the Ben McKay in 1998. And they show an excellent performance in terms of error rate, error flow, and rate of convergence with iterative decoding. But they're not perfect, as their main setbacks are large hardware decoder complexity and the size of memory required for storing this message. Now, the main decoding schemes for LPC codes include the sum product algorithm, which is a probabilistic decoding algorithm that's based off base pairing. Its modification for non-binary codes is referred to as Q-array sum product algorithm, which is QSPA for short. Variations include the log SPA and the fast Fourier transform Q-array sum product algorithm. Another famous decoding algorithm is the min-sum algorithm, which is a probabilistic decoding algorithm that's based off log likelihood ratios. Its variations include the simplified min-sum and the extended min-sum. Now, research in these two codes has, when compared to each other, shown that the sum product algorithm has a better performance in terms of its bit error rate. However, it suffers from complexity when compared to the min-sum algorithm. Now, this trade-off of complexity against performance is a major issue when it comes to not only decoding of LDPC codes, but codes the codes in the field of forward error correction in general. So, a lot of research has been invested into trying to get an algorithm that is low in complexity but high in performance, which brings me to my my research, which starts with the RID scheme. What RID stands for is revolving iterative decoding scheme, and what it is a reduced complexity algorithm for decoding of LDPC codes. Now, how it works is that it takes a small submatrix of your parity check matrix and works on it in a revolving manner. I will better explain this as I continue with my presentation. Now, the RID scheme has been shown to reduce the hardware and implementation complexity. It's also been shown to reduce the size of memory required to store information while decoding. However, its major disadvantage is that it's only applicable to codes that have parity check matrices defined by a block cyclic structure, which caused more research to be done, and then the CPM RID scheme was devised. What CPM stands for is circular permutation matrix, and then RID scheme, and what it is just a variation of the RID scheme for QCLDPC codes, as QCLDPC codes are defined by parity check matrix that has CPM structure. Now, to help understand how the CPM RID scheme works, we have to understand the structure of the parity check matrices. Now, how the structure is composed of small submatrices, and all these submatrices are either CPMs or zero matrices with dimensions of Q-1 by Q-1. What Q is the size of the field. If you're working in a field of GF16, then Q is going to be 16, and your CPMs are going to have the dimensions of 15 by 15. If you're working in a field of GF8, then Q is going to be 8, and your parity check matrices are going to be 7 by 7. Now, the CPMs that we're going to use in our research are special CPMs that are referred to as alpha multiplied circular permutation matrices. What these CPMs are like if you were to select any row on the matrices, it would basically be the previous row shifted one place to the right, multiplied by alpha, where alpha is the primitive element of the field. Now, this, because they are made of small submatrices, we can divide them into row blocks, as shown here. So you'd have a row blocks reaching m with the length of, and column blocks with the length of n, where m and n are the dimensions of the base matrix, which is now another concept. I'd have to spend more time explaining, and unfortunately I only have 12 minutes. So now, to understand how the CPM would work, a section-wise cyclic shift has to be performed. What this is, for instance, if I was to take any row block and take the first row only of the row block and shift it within the section, and when I say section, I mean like within its own matrix, and shift it one place to the right and multiply that by alpha, I'd get the next row because of the CPM structure of the H matrix. And if I did this Q minus 2 times, I'd be able to get all the rows of my CPM based off one row, if that makes sense. Now, if I do this simultaneously for the whole matrix, I get all the rows based off just a couple of rows based on my row block structure. Now, how the CPM works is a matrix called the H star is defined. What H star is basically you take your row blocks and take the first row of each row block. Now, with this, you can shift them, you perform a sectional cyclic shift, Q minus 2 times on H star, you can get all the rows of your parity check matrix. I hope it makes sense. Now, when you're decoding, you decode based off your H star matrix instead of your full H matrix. So if I'm working, for instance, in a field of GF16, and I have 4 row blocks, which means I'd have 60 rows. Instead of using all those 60 rows in my decoding, I'd only use 4 rows and feed that into my decoder. So if I had my reliability information from the channel, I'd feed it based on my H star into my decoder and update the information with whichever decoding scheme I have. Once I update that information, instead of performing the next iteration, I shift the information one place to the left and perform another iteration. Now that's what is called as decoding sub-iteration. And if I do that Q minus 2 times, it will be the same as performing one iteration. So if I perform Q minus 2 sub-iterations, I would have worked on my entire parity check matrix in the form of one iteration. And this is basically how decoding with the CPM RID scheme works. Now, research on this has been done when applied to the min-sum decoding algorithm for binary QCLDPC codes and the min-max decoding algorithm for non-binary QCLDPC codes. The results have been good because it's reduced the computational and implementation complexity plus maintained the performance of the given decoding algorithms. For my research, I intend to use the FFT QSPA, and the reason I'm using the fast Fourier transform version of the QSPA is because it is one of the best, if not the best, decoding algorithms in relation to LDPC codes. So if we are able to reduce the complexity of this and maintain the performance, this would be a step forward in the right direction. Now, the methodology for my research is that I will generate a random message and pass it through an encoder. I will use a 16-core modulator, then an AWGN channel, then demodulate the signal and compare the results for both FFT QSPA and my CPM RID QSPA. Finally, I'll check the bit rate performance of each to see what performance gains would have attained. So finally, my research question is basically what performance and computational complexity does the FFT QSPA attain when incorporated with the CPM RID? Before I can continue this, just give a small side note in that only recently we stumbled upon a paper where they had incorporated the CPM RID with the FFT QSPA. However, there were small differences compared to what we are doing with what we are doing. Like for instance, the mode of construction they used for their QCLDPC code is different from the one we're using, and they also use it on our BPSK modulation scheme. And what we're using is a 16-core modulator. Some of the benefits of using a 16-core modulator is that it has a wider bandwidth compared to PPSK, which enables you to pass more information. So some of the results found with this would be more practical in today's world where everyone wants to pass a lot of information as quick as possible. And with that, I will ask for any questions.
Thank you. So we have time for questions. I have a question myself. So you look at highly structured matrices, right?
Yeah.
So there's quasi-cyclic property.
Yeah.
There's also been work in the past by people like Richardson and Urbanke who advertised irregular structures of matrices, irregular LDP sequence.
Oh, irregular, yes.
Yeah. Can you say anything about the trade-off there between
with irregular LDPC codes, performance with such codes is actually better than regular LDPC codes. However, the construction and decoding is more complex compared to when you're dealing with regular LDPC codes.
to get a trade-off?
It's the trade-off, yeah.
Other questions or remarks? If not, then thank you very much again. The next speaker to come forward to set the presentation is MK Johannesburg from the University of Johannesburg. This will be joint work with Theo Swart and